Okay, everybody. Today we're going to be talking about well-founded posets. So remember last time we talked about the definition of a poset and gave some examples. Now we're going to talk about specific types of posets called well-founded posets, which are particularly nice. In fact, as we'll see later, very precisely, they're exactly the posets where you can do induction. Okay, so to start off, we have a proposition. So let x, let be a poset, and then the following are equivalent. So sometimes mathematicians write TFAE, and this means the following are equivalent. So number one, every non-empty subset S of X has a minimal element. And here minimal means an element X, so that if I have some Y that's in S, so an element X in S, so if I have some Y in S and Y is less than or equal to X, then actually Y must be equal to X. This is not saying that the element X is less than or equal to every element of S. It's just saying that there is no element of S that's smaller than X, strictly smaller than X. And those are two different things when you have a poset, as opposed to a totally ordered set. So that's condition number one, and then condition number two is that X satisfies the descending chain property. So that means that there does not exist an infinite, strictly decreasing chain in X. So that would be a chain like x0, x1, x2, where x0 is strictly bigger than x1, and x1 is strictly bigger than x2, x2 is strictly bigger than x3, etc. in X, in the poset X. So that such a chain does not exist. And so if a poset satisfies either of these conditions, then it's called well-founded. And in the case, I should have said this, in the case of a total order, so if this is a totally ordered set, then you call it well-ordered. So let me put that in parentheses here. So if this is total, we call it well-ordered. So you may be more familiar with that word. Great. Okay, so here's two examples of well-founded, in fact, well-ordered and not well-ordered posets. Example number one is the natural numbers with the usual order is well-founded, well-ordered because it's a total order. So here I've drawn the natural numbers, and I've drawn the Hasse diagram, because I've only drawn the first two elements. But as you can, so in the natural numbers, right, let's just check that condition 2 holds. So we just want to check that there does not exist an infinite strictly decreasing chain of the natural numbers. And this is pretty clear. x0 has to be some n, and then x1 has to be strictly less than n, so I have to decrease. And at some point I hit 0, or I hit 1, and then I can't go any smaller. Awesome. So it is well-founded. On the other hand, z, which I've drawn as the full diagram here, z is, with the usual order, is not well-founded, precisely because of this, right? There certainly is an infinite strictly decreasing chain in z. I can take this to be 0, -1, -2, etc. Awesome. Okay, so on the next board, we're going to prove our proposition. Okay, so let's prove it. So first, let's start with 1 implies 2. And we're actually going to prove the contrapositive, not 2 implies not 1. So suppose not 2 holds. So that means there exists an infinite strictly decreasing chain inside of S. X0 greater than x1, greater than x2, etc. But then if I just take the set x0, x1, x2, etc., this set of elements, this is a non-empty subset of X, and it does not have a minimal element because it consists exactly of the elements in this chain, and each element of the chain has something smaller than it. So there's no minimal element. Great, okay. That's 1 implies 2. Let's now do 2 implies 1. We're going to do it by contradiction. So suppose that 2 holds, but 1 does not. So that means that there exists some non-empty subset S, which does not have a minimal element. So because S is non-empty, that means there exists some x0 in S, right? There's some element of S. And because S has no minimal elements, that means there must exist some x1 in S which is strictly smaller than x0. But of course, S still has no minimal elements, and x1 is in S, so that means there's an x2 that must be strictly smaller than x1, and you just keep doing this forever. You can just keep producing xi's, which are smaller than xi minus 1s. You can continue forever, you obtain an infinite strictly decreasing chain, violating number 2. Excellent. Okay, so now we're going to have a few more examples of well-founded and non-well-founded posets. And this will lead to sort of a method of producing well-founded and non-well-founded posets from other ones, which is kind of cool. Okay, so the first example that I probably should have mentioned before is that all finite posets are well-founded, right? So remember, one of the conditions for being well-founded is that it satisfies the descending chain condition. So finite posets definitely satisfy the descending chain condition because I can't have an infinite sequence of elements that are not equal, let alone decreasing, strictly decreasing. Great. Okay, so here's another example. So remember that we said that the natural numbers with the usual order is well-founded. So I can take the product of the Cartesian product of the natural numbers with itself. That's a set, and then I can put a partial order on it as follows. So remember that elements of the Cartesian product are pairs of natural numbers. So I have a pair n comma m is going to be, oh, that kind of looks a little sloppy. So a pair n comma m is less than or equal to a pair n prime comma m prime if and only if n is less than n prime and m is less than m prime. So you just check each coordinate separately. This is called the dominance order sometimes. It's also called the product order. So it turns out that if I take n cross n with the product slash dominance order, okay, let me write that down. I'm just going to write down the product order. Product or dominance order. Great. Right. So it turns out if I take n cross n with the product slash dominance order, this is also, oh, I wrote well ordered, but it's not. It's well founded. That was the whole point. It's well founded. Not well ordered. So it's well founded. You can I've drawn the Hasse diagram, and you can see that there's a bottom element 1, 1, and it kind of goes up from here in like a cone shape, or a triangle shape. And because the Hasse diagram is not linear, it's not just a single line, then it's not a totally ordered set. And so I should be saying well founded, not well ordered. So in general, when I take the product order on two linearly or two totally ordered sets, the result is not necessarily a total order. But in this case, I started with well-founded. The product is still well-founded. Okay, so as another example, let's take z, the integers with the usual order. We saw before that this is not well-founded because it had a strictly infinite decreasing chain, which was just 0, -1, -2, -3, etc. With the dominance slash product order, the product of z with itself is again not well-founded. And I've drawn some of the Hasse diagram here, and it'll continue forever downwards. An example of a strictly infinite decreasing chain, or an infinite strictly decreasing chain is like if I do like 1, 0, and then like 0, 0, and then -1, 0, and then -2, 0. That's going to be strictly decreasing. And then, okay, great. So we'll now see that actually this is exactly what happens in all cases. If I have two posets and I take their product poset, then the result is well-founded if and only if each of the original factors is well-founded. That's what we'll see next. Okay, so on this board, we're going to completely generalize the examples that we had on the previous board. So if x and y are two posets, then I can define a partial order on their Cartesian product, which is called the product order. And it's defined by if I have a pair x comma y, which is in x cross y, and a pair x prime and y prime in also in x cross y, then we say that x comma y is less than or equal to x prime comma y prime if and only if x is less than or equal to x prime and y is less than or equal to y prime. So you just check the factors individually. Okay, and then the proposition is that if I have two non-empty posets, then the product order on x cross y is well-founded if and only if each of the original ones are also, each of the original ones is also well-founded. Okay, so now we're going to prove this proposition. First, we're going to prove this direction. So that's if x and y are well-founded posets, then the product is also well-founded. So let's prove the contrapositive. Suppose that x cross y is not well-founded. By one of the equivalent definitions of well-founded, that means there exists an infinite, strictly decreasing chain inside of x cross y. So that's a sequence of pairs x0, comma y0, which is strictly bigger than x1, comma y1, which is strictly bigger than, etc. Great. Okay. So this does not automatically. So right, this gives me two chains, one in x and one in. Oh, this looks like an x. This is supposed to be an x, but it looks like a y. This gives me two chains, one in x and one in y. So I have my chain x0, x1, x2, etc. in x, and y0, y1, y2, etc. in y. But just because this is strictly bigger than this, that does not necessarily mean that x0 is strictly bigger than x1 and y0 is strictly bigger than y1. It means that one of those must hold. They both could hold, but at least one of them must hold. So it must be that x0 is strictly bigger than x1 or y0 is strictly bigger than y1, but we don't know that both of those strict inequalities hold. But we're trying to find an infinite, strictly decreasing chain in either x or y. So let's look at this one, at chain number 1, which is inside of x. So what it means for such a chain to stabilize is after some point n in the sequence, then all of the terms of the sequence are just equal. So suppose that this doesn't happen. So suppose that this chain does not stabilize inside of x. So that means it actually has a subchain that is infinite and strictly decreasing. Right, that's the opposite of what it means to stabilize. And that's great. So if I obtain a subchain that is infinite and strictly decreasing, that gives me a chain inside of x that's strictly decreasing, and so x cannot be well-founded, which is what we're trying to show. Okay, so that's one case. But now suppose that it does stabilize, that 1 does stabilize. I should write 1 there. Let's do that. So suppose that 1 does stabilize. So that means that there's some point in the sequence so that xn is equal to xn plus 1 is equal to xn plus 2, etc. Off forever. Right? The chain becomes constant. Well, then because x of m, y sub m is strictly bigger than x of m plus 1, y sub m plus 1 for all little m greater than or equal to n, or by hypothesis, this is strictly decreasing. Well, if this is strictly bigger than this, but xm is equal to xm plus 1, since the chain stabilized, that must mean that ym is strictly bigger than ym plus 1 for all m greater than or equal to n, and so yn, strictly bigger than yn plus 1, strictly bigger than etc., is an infinite, strictly decreasing chain inside of y. So what we've shown is that if the product is not well-founded, then either I can find an infinite, strictly decreasing chain inside of x, or I can find an infinite, strictly decreasing chain inside of y. So one of x or y must be not well-founded. Great. Okay, on the next board, we'll prove the other direction. Okay, so here we have the second direction. I rewrote the proposition here, and it is unfortunate that real life does not work the same way as an iPad, so I couldn't just select it and move it up. Maybe someday they'll have, giant iPad blackboards. Okay, so here's the rest of the proof. So this is this direction, and so that means we're assuming that x and y that the product is well-founded, and we're trying to show that x and y are also well-founded. And so again, we're going to prove the contrapositive. And so what that means is that one of x and y must be not well-founded, and we're going to try and show that x cross y is then also not well-founded. Okay, so suppose that either x or y is not well-founded. Without loss of generality, we can assume that y is the one that's not well-founded. So what that means is there exists an infinite, strictly decreasing chain inside of y by one of the equivalent characterizations of well-foundedness. So this is the chain y0 greater than y1 greater than etc. off forever. But since x is non-empty, there exists some x0 in x, and here we can actually use the non-emptiness explicitly. So there exists some x0 in x, and so I can just form the sequence x0, y0, x0, y1, x0, y2, etc. And this is a decreasing chain because, so this is bigger than or equal to this, because, well, x0 is bigger than or equal to x0, and y0 is strictly bigger than y1. And so in the product order, this is bigger than this, and it's strictly because they're not equal, right? y0 is not equal to y1. And etc., right? The rest of them are also strictly bigger. So this is an infinite, strictly decreasing chain inside x cross y. So x cross y is then also not well-founded, which is what we wanted to show. Amazing. Okay, so for the rest of this video, we're going to talk about a very important example in the theory of posets, which will end up being a well-founded poset. So it's a perfect example to finish up our video on well-founded posets. First, let's define a partition of a number. So a partition is just a finite list of natural numbers. So n1, n2, nl, so that it's ordered, biggest to smallest. So n1 is greater than equal to n2 is greater than equal to greater than equal to nl. And so this sequence of numbers, this list of numbers, is called a partition of the number that is the sum of those entries. And its length is just L. It's just the number of numbers in the list. And to any partition, you can associate a Young diagram as a way of sort of picturing what a partition is. So what do? We just arrange some boxes. In the first row, we have n1 boxes. In the second row, we have n2 boxes, and then the last row, we have nl boxes. And so there are L rows. So the length of the partition tells you, it's a very bad L. The length of the partition tells you the number of rows, and then the entries in the partition tell you the length of each row. And so notice because n1 is bigger than n2, bigger than nl, the top row is the biggest always, and then the next row is smaller, not strictly smaller. Okay, and then y will denote the set of all partitions. So y is a very big, it's an infinite set. There are lots of partitions. Because we haven't specified that the elements of this are partitions of a particular number. These are just all partitions of any number. So for example, 5, 4, 3, 3, 1, this is a partition because, right, 5 is bigger than 4, which is bigger than 3, which is bigger than or equal to 3, which is bigger than 1. And it's a partition of the number 5 plus 4 plus 3 plus 3 plus 6 plus 1, which is hopefully 16. And it has length 5 because there are 5 numbers in this list. So 1, 2, 3, 4, 5. And its Young diagram looks like this. So there are boxes. The top row has 5 boxes corresponding to this 5. The next row has 4 boxes corresponding to this 4. The next row has 3 boxes corresponding to this 3. The next row has 3 boxes again corresponding to the second 3. And then the last one has 1 box corresponding to 1. Okay, so we're in the video about posets, in particular well-founded posets, and so we should definitely define a partial order on the set of partitions, in keeping with our theme. So there's a partial order on y, which is called the dominance order, and it's defined as follows. So here's a partition, and here's a partition, and we say that this partition is less than this partition in the dominance order, if and only if k is less than or equal to L, and Right, so that means the length of this one is smaller than the length of this one. And for each mi, the corresponding mi should be smaller than the corresponding ni. And so, like pictorially, this is very easy to understand what this is saying. It's just saying that the Young diagram of this one will fit inside the Young diagram of that one. If I look at, if I align their two top left corners. And so the Hasse diagram of this poset is called the Young's lattice, and here I've drawn out the first 3 rows, I guess, 4 maybe. So at the bottom we have the empty partition, which has no numbers at all, and then we have the partition 1, and I should write that actually. This is the partition 1. This is the partition 1, comma 1, and this is the partition 2, and then this is the partition 1, 1, 1, and 2, 1, and 3. And so you'll notice, I probably should also write the arrows. Always nice to see those arrows. Although at some point we're definitely going to get lazy and forget to write the arrows. So notice that like on the 0th level there's no numbers in the list, but at the 1st level there's the number 1, and on the 2nd level if I sum up all the entries, I'll get the same number. And same with the 3rd level. If I sum up all the entries here, I get 3. Sum up 2 plus 1, that's 3, and 1 plus 1 plus 1, that's 3. So that means on the nth level, every partition on the nth level is a partition of n. And so a good exercise to check your understanding of partial orders from the beginning of the video is just to show that, or I guess from the previous video, is to just show that the dominant order is actually a partial order. And I actually wanted to say, so let's just quickly look at why is this less than or equal to that in the dominance order? Well, it's because if I compare this Young diagram and that Young diagram, this one fits inside of that one fully. And same with this, like why is this partition less than or equal to that one? Well, this fits inside of this, and this also fits inside of that. That's why this is less than this. But for example, this is not less than or equal to that because it doesn't fit inside of it. Right, if I align the top left corners, this would have a box sticking out from the bottom. Awesome. Okay, on the final board for this video, we have the theorem that the Young's lattice with the dominant order is a well-founded poset. Hence why it is appearing in this video. So here's the proof. It's quite easy actually. So if I take any partition in Young's lattice, notice that there are only finitely many partitions that are smaller than it in the dominance order. And this is because, remember, smaller than in the dominance order means that the Young diagram for the smaller one fits inside the Young diagram for the bigger one. And of course, there can only, given any Young diagram, there's only finitely many boxes, so you can only have finitely many small Young diagrams fitting inside of it. But that means that there cannot be an infinite strictly decreasing chain inside of this poset, because if I have a chain, right, I start at the top element, that's some partition, and then everything smaller than it is less than or equal to this in the partial order, but there's only finitely many things less than it anyway. So therefore this must be, right, by our theorem from a few boards ago, well-founded is equivalent to there being no infinite strictly decreasing chains. So it's a well-founded poset. Excellent.